हेलो फ्रेंड्स, टुडे वी विल डिस्कस द वेपर पावर साइकिल। पहले तो हम लोग सिंपल थर्मोडायनेमिक साइकिल क्या होती है समझते हैं। हम लोग थर्मोडायनेमिक साइकिल में नंबर ऑफ प्रोसेसेस पढ़ते हैं, जैसे कांस्टेंट प्रेशर प्रोसेस, कांस्टेंट वॉल्यूम, थर्मो एडियाबैटिक प्रोसेस, आइसोथर्मल प्रोसेसेस। तो अगर हम इन सारी प्रोसेसेस को एक सीक्वेंस में अरेंज करें सच दैट द इनिशियल एंड फाइनल स्टेट आर सेम, देन इट इज कॉल्ड थर्मोडायनेमिक साइकिल. So when a system undergoes a sequence of thermodynamic processes, such that the initial and final state is same, then it is called as thermodynamic cycle. The basic thermodynamics we have studied, that is Carnot cycle, in which we use two isothermal and two adiabatic processes, and we can see that it is in which the initial and final state are the same. So it is a thermodynamic cycle. So broadly, thermodynamic cycles are classified as follows. So in thermodynamics there are two types of cycle, that is power producing cycle and power consuming cycle. So generally power producing cycle are simple heat engine. So we know the heat engine in which there is a lower temperature and there is a higher temperature. This is T lower and this is T higher, and work is produced when heat is supplied. And the second is gas power cycle, in which we use the gas as a fluid, and this is the example of Brayton cycle, that is gas which is works on Brayton cycle. एंड वेपर पावर साइकिल जो कि आज हम लोग डिस्कस करेंगे, दैट इज जनरली वी यूज रैंकाइन साइकिल एज अ वेपर पावर साइकिल. It is Rankine cycle. And in refrigeration, that which are the power consuming, in which the power is supplied to the device, and then the heat extracted from the cooling medium. So the vapor compression refrigeration cycle is a simple example of the power consuming cycle. Now the vapor power cycle, in which the fluid is generally used as vapor, which is the which changes the phase, that is fluid which changes the phase. And generally steam is used in vapor cycles. Vapor power cycles. Steam, because the steam has low cost and is available easily. Steam low cost and due to availability, we use it. So the Rankine cycle works on vapor power cycle, or example of a vapor power cycle. Now these vapor power cycle generally used in thermal power plant, that is application which is the thermal power plant, thermal power plants. So therefore we in this video we introduce some basic concept of thermodynamics, the thermal power plant. So this is the simple thermal power plant in which there is a boiler and boilers generate steam and which goes to the turbine, and from the turbine it goes to the condenser, and from condenser to pump. This is produce work WT, pump is consume the work, that is WP, and heat supply to the boiler and heat rejection from the condenser. So we start from the turbine, that is if this is point 1. So here the steam is high temperature and high pressure. So steam is high pressure and temperature. So when it is enter the turbine, it expanded, and after expanding it is low pressure and temperature, that causes it produces work. So turbine is a simple rotor in which several rotating blades are arranged such that it produces work by expanding the steam. So हम लोग ज़्यादा डिटेल में नहीं जाएंगे टर्बाइन के, we just overview it. After that the turbine it goes to a condenser where the steam is condenses, that is here the steam is saturated, that is it enters in turbine which is at superheated. So here is a mixture of vapor plus water, so and here it condenses and it is saturated liquid at this point. This is saturated liquid and pressure is constant because condenser is a steady flow device. So after the condenser it goes to the pump, and in pump the pressure raises and pump the water to the boiler. So here pressure is high or raises and temperature is almost constant because the water is an incompressible fluid. So temperature almost constant, temperature is almost constant, and in boiler heat is supplied, so its temperature and pressure is also increases. So after boiler the steam is generated which has high temperature and pressure. So this is the simple overview of a thermal plant. Now if we write down the network of the cycle, the network which is the W net, it is turbine work minus pump work, or heat supplied or heat added to the boiler, heat added to the boiler. So this is QS. Then the efficiency of the cycle, which is the W net divided by QS, that is heat supplied. And from the first law of thermodynamics, net heat, which is this is Q net, this is Q supplied minus Q rejected. If the heat rejected from condenser is QC, so again we can write it QS minus QC divided by QS, that is this is QC minus QS. So in the thermal power plant, we can see the pressure is dropped in turbine and raises in pump and in constant in boiler and condenser. So the pressure which is constant in boiler and condenser and pressure raises in pump and pressure decreases in the turbine. So pressure dropped in turbine. Now if हम लोग इस जो थर्मोडायनेमिक साइकिल अगर इसको प्लॉट करें टीएस और पीएस डायग्राम पर, देन हम लोग पाएंगे रैंकाइन साइकिल. So Rankine is a scientist which plot this cycle on a TS diagram. So we have two levels of pressure. We have two pressure levels. This is T and this is S. So this is two-phase liquid, that is vapor plus water. So there is vapor dome and the pressure levels. So this is the constant pressure line on TS diagram. Now the process 1 to 2 is expansion. That is 1 to 2 is expansion. So if steam is saturated, then the point 1 is here, that is saturated vapor, and if it is superheated, then point 1 is here. So this is 1 and this is 1 dash. Now the 2 to 3 is, this is the condensing process at constant pressure. This is 2 to 3 which is condensing, and 3 to 1 is isentropic compression in the pump. So this is 3 to 4, and 4 to 1 is constant pressure heat addition in boiler. So this is the simple Rankine cycle, and in this we consider turbine as a insulated. So this is this considered as insulated, because we doesn't want to lose any work. Now The process 1 to 2 is isentropic expansion. 2 to 3 is constant pressure heat rejection in condenser, and 3 to 4 is isentropic compression, and 4 to 1 is the constant pressure heat addition. Constant pressure heat addition. Now if we draw this cycle on this is HS diagram, that is at HS coordinate, we get this is so the Vapour dome looks like this, and constant pressure line on HS diagram which is expanding. So this is the constant pressure line, that is. Now if steam is saturated, then this point is 1 dash and expansion in this way. If steam is superheated, then this point is 1. 1 to 2 is expansion, 2 to 3 is heat rejection, 3 to 4 is the isentropic compression, and 4 to 1 is heat addition. So this is the Rankine cycle on HS plane. This is the Rankine cycle. Now we calculate the enthalpy at different points. This is the QS, this is QR or QC. This is WT. Now the turbine work, which is the H1 minus H2, that is, it is a steady flow device, and we consider as the kinetic and potential energies are negligible. So Ke is equal to T, which is 0, and pump work, which is H4 minus H3, heat supplied, which is H1 minus H4, heat rejected, which is H2 minus H3. So this is yes, this is. Now the efficiency. Efficiency of the Rankine cycle, which is the net work on heat supplied, that is turbine work minus pump work on QS. So this is turbine work, which is H1 minus H2, minus pump work, which is H4 minus H3, and the heat rejected, which is H3 minus H2. This is the efficiency of the Rankine cycle. So the H1 we can see from the steam table. So at given temperature and pressure, H1, which is the from steam table, So at that temperature and pressure, H3, which is the HF, this can also be calculated from steam table. Now the process, now we have to calculate the dryness fraction. So if we see the cycle, so here at point 2 there is a wet steam. So x is the dryness fraction. तो हमें ड्राइनेस फ्रैक्शन कैलकुलेट करने के लिए एंट्रोपी को इक्वल करना पड़ेगा, क्योंकि एंट्रोपी 1 and 2 पर सेम रहेगी, बिकॉज प्रोसेस 1 and 2 इज आइसेंट्रोपिक. सो वी इक्वेट द S1 and S2, and S2 can be written as SF plus X into SFG. So from here we can calculate the dryness fraction, and when we calculate the dryness fraction, then we can calculate the H2, that is HF plus X HFG. Now next is how we calculate the pump work. So for the pump work, so we apply the TDS equation, that is TDS is equal to DH minus BDP. So for isentropic process this will be the 0. DH is equal to BDP. If we integrate 3 to 4, then we get H3 minus H4 is equal to the, this is 3 to 4, this BF is equal to DP. So BF is equal to, this is B3, that is saturated liquid. So H3 minus H2 is equal to H4 is equal to the, this is B3, and this is pressure, that is P4 minus P3. So in this way we can calculate the pump work. Now we solve the question on the simple Vapour simple VCR simple Rankine cycle. So here is the question. So in given question of thermal power plant which working on simple Rankine cycle, the steam enters in a turbine at 3 MPa and 350 degrees centigrade at superheated state. The condenser is at pressure of 75 kPa. Then we have to determine the work output, net work output, and thermal efficiency. So first we draw the cycle on TS plane. So this is the Rankine cycle. This is point 1, 2, 3, 4, and here is dryness fraction is X. This is T and this is this, and this temperature is 350. This is 350. The pressure is 75 kPa, and this is 3 MPa. So from the steam table at 3 MPa and 350 degrees centigrade, the H1, which is the 311, 5.3 kilojoule per kg, S1 which is 6.7428 kilojoule per kg Kelvin. Now properties at 75 kPa. So here the H3 is equal to HF, which is the 384.39 kilojoule per kg, and SF is equal to S3, which is 1.2130 kilojoule per kg Kelvin, HFG. So write the next piece. HFG, which is the 2278.6 kilojoule per kg, and the SFG, which is 6.2434 kilojoule per kg Kelvin. Vf is equal to V3, which is 0.001037 meter cube per kg. So these properties are taken from saturated steam table, that is saturated steam table, and this one are taken from superheated steam tables. Now process 1 to 2 is isentropic. So S1 is equal to S2, and S2 can be written as SF plus X SFG. So if we substitute the values, that is 6.7428 is equal to SF, which is 1.2130 plus X into 6.2434. Then we get X, that is Raynaud's fraction, which is 0.885. Now H2, that is enthalpy as state 2, which is HF plus X into HFG. So H2, which is the 384.39 plus 0.885 into 2278.6. So we get enthalpy at state 2, which is 2400.95 kilojoule per kg. Now the pump work. Which is WP, that is V3 into dP, that is change in pressure, that is V3 into, this is P4 minus P3. So this is the V3, that is specific volume at state 3, which is 001057. Pressure, that is 3 ampere, that is 3000 kPa minus 75. So we get pump work, which is 3.033. This is kilojoule per kg. Now pump work, which is the 3.3033. so this can be written as H4 minus H3 in terms of enthalpy. That is H4 minus H3, which is 3.33, and H3 we know, so H4 is equal to, this is 3.033 plus H3 is, this is 384.39, so this is the 387.423 kilojoule per kg. Now the turbine work. Which is Wt, that is H1 minus H2, which is 3115.3 minus 2400 point, this is 15. So we get turbine work, which is Wt is equal to 714.35 kilojoule per kg. Now pump work we have already calculated. Pump work, which is Wt, which is 3.033 kilojoule per kg. So now the net work, which is the W net, that is turbine work minus pump work. So this is 714.35 minus 711 point, sorry, this is the 3.033, so this is 711.317 kilojoule per kg. And heat supplied to the boiler, which is Qs, that is, this is H1 minus H4, so this is 3115.3 minus H4, which is 387.423. so heat supplied, which is 2727.872 kilojoule per kg. Now efficiency, that is cycle efficiency or Rankine efficiency. Rankine efficiency, which is the eta R. So this is W net, that is network and divided by heat supplied. So network is 711.37 divided by 2727.872. so this is the 0.26, or this is 26%. so this is the efficiency of the Rankine cycle. So this is all about the vapor power cycle based on the Rankine cycle. So thank you.